So for MP3 this week, your team is finally going to get the opportunity to do some microarchitectural design exploration, some implementation for our vertex shaders and our programmable shader cores. Before you dive into that, I think it's important that we review what's new in the MP3 in terms of the driver infrastructure and to look at some of the design decisions that are going to directly influence what you'd like to do as you implement the shader core ISA that we've provided for you. The first thing you may notice when you take a look at what is new in the MP3 repository is we have a new file in our lib SGP driver. This is our sgp_shaders.c. And for the most part, this will be the only driver file that you'll be editing for this assignment. It looks very similar to what we've already had and what you've already been playing around with the graphics side. And arguably, it all could have been included together in one file. But there was enough functionality for what's happening just on the shader organization side of things from the driver's perspective. I separated that out as its own separate file. So this is our SGP Shaders.c. And a lot of what you'll see at first is a lot of sort of bookkeeping code, very similar to mirroring the functionality that your OpenGL driver would require to have for just keeping track of the shaders in the system. So you'll see these functions as we have. They're a little bit abstracted away in a separate little library for loading shader code, but creating programs, creating shaders, attaching shaders to those programs, compiling them and linking them all together. A lot of those early functions, creating program, are just allocating IDs in the OpenGL and in our driver ecosystem. But it's GL compile shader and SGP GL compile shader where the actual magic is happening here. So it's going to be taking those files, those .vert and .frag files that we've been using all semester, mostly in pass-through mode up until this point, and it's going to generate, in our case, a binary that's going to be our target for implementation in hardware with our vertex shader. While you're not going to be doing a ton of editing on this file this week or this assignment, you do have to become pretty familiar with what's happening in this function and a couple of the companion functions, because certainly when MP4 comes and we're going to kind of replicate a lot of this infrastructure and expand some of these functions, you're going to be wholly responsible for that. So like in MP1 and maybe to a lesser extent in MP2, having someone who's really dedicated to knowing the ins and outs of the driver and influencing the hardware design decisions based on what's happening in the driver is an important role to consider. So a lot is happening in this compile shader. I'm not going to walk through every line of it and what's happening, but at a high level what is happening is we're calling a library to actually compile from GLSL to this SPIRV format. And that's what's happening here. It's using the Google Shader C project, which is specifically for managing a couple of different compilation frameworks and kind of gluing them together correctly. So we're taking advantage of that. And our output of that step is SPIRV disassembly. And I'll show you in a moment what that looks like, but we've seen it in the lecture very briefly as well. It's a disassembly format that looks a little different than the assembly formats that maybe you've played around with in the past. But if you've looked at LLVM output, it's very similar to what you would get out of something like that. We then take that as our input to what we're calling, quote unquote, our compiler. It's really more of an assembler, but it's taking that SPIRV format and generating instructions that are appropriate for the hardware that we have in place. That is not happening directly in this C file, but this C file is referencing in the relative path a Lua script that we're using to do the compilation for us. And then the rest of this code is really launching that Lua script, passing it input values like what is the actual source, where should we be putting some objects in memory for us, and actually just calling it and getting results back out, and then managing the results of that. We don't also need to walk through the entirety of this Lua script as well, but if you have questions and you think something is ambiguous in the documentation with regards to, well, what is the opcode of my floating point multiply instruction? Well, here's the definitive answer. The Word document or the PDF may say one thing. Someone else may say something else on Discord. If we're calling this script, this is what the opcode is going to be emitted for those particular instructions. There's no magic to it here. It's really just taking a look at what operations this SPIRV is dictating and connecting that to a format that makes sense for how we have designed our SGP infrastructure. This code will get run, this driver code will get run, so we've updated the makefile as well, when you're running any of the OpenGL applications that are linked against the lib SGP driver. So you'll be able to see that right away. By default, they are all running create program, attach program, compile shader, doing all those kind of things. And you'll see the output as debug output. You also don't have to run OpenGL code to see how this compiler is operating. we have provided, just as part of MP3, one additional kind of standalone application that I'm just calling GLSLC test for the GLSL compiler test that allows us, independent of running an OpenGL application, to just load up both a vertex and a fragment shader. Modern OpenGL requires we always have both, and to see what the compiler is doing on it. So if you're not sure, you're making a one-line change to your shader because you want a slightly different effect, and you don't just want to blindly test it, you want to see what the actual assembly output is going to be and what you're going to have to be able to support for your implementation, you'd potentially want to run this application beforehand and get a good feel for what the compiler can handle, where it fails. You'll find some failure conditions, I'm sure, and what kind of output you get after you're done with it. So here's an example running it. But before I run it here, this is run with a new shader that's provided as part of MP3 as well. It's not doing that much. We could open it up separately, but actually the output of this tool in debug mode will show us what shaders it's taking as input. So if you were to look at the source code for this application, the GLSLC test, it's not doing much. It's running create program, create shader, shader source, linking them all together, and generating the output from the compiler infrastructure. So it's very similar to what's happening in your OpenGL applications. This just isn't even creating an OpenGL context in the first place. This is just playing around with shaders. So it's a nice standalone thing. You don't need to be connected to the remote desktop infrastructure to be able to run this. You can do this from any command line terminal, and if you have that set up, it should work just fine. So this does provide you, as part of the debug output, what the actual shader source is. So here's our vertex shader. This assignment is only operating on vertex shaders, although we are also compiling the fragment shaders. So you can pass it any fragment shader you want. The examples directory in this utility has all sorts of shaders we've provided, but they're all going to be effectively passed through in our hardware for MP3. And in MP4, we're going to change that assumption. But this is our vertex shader for this example here. And it's taking our input vertex that's specified in the OpenGL application and just doing some simple multiplications and additions. X scale. So scales the X dimension and scales the Y dimension. We could do this with a matrix, but it's doing so with individual scalar values here. And then it's also translating it as well. And then finally, it just passes the color input as output. So it's, from a color perspective, it's a pass-through shader. From the positional data, it's doing some very simple transformations on it. This becomes important when we look at how we do that in our shader code. And as we will get a chance, if we haven't done so already, to talk about in class, you do so by passing these as uniform inputs to it. We have our inputs and outputs in terms of input vertex and transformed output vertex information, some of which we have to explicitly specify. Other things are just sort of required outputs of our vertex shader. And then separately, we have this ability to specify, here is some shader data. It's uniform, meaning for every invocation of the shader, for all the vertices for a given draw call, they all get the same values for those. They're uniform across the draw call. But those are regions in memory. We have to allocate them. We have to, in OpenGL, set values to overwrite what's in those locations in memory. And then the shader core itself is responsible for grabbing it and doing that processing. So that, at first, it shows us what the actual shader source is for both the vertex and the fragment shader. Here it's showing us what the SPIRV output is going to look like. It's not unreadable, but it is pretty verbose in terms of how it's being very explicit about every operator, every register, every operation that's happening. So it is a lot to kind of go through. What you'll then see, and probably most importantly for your debugging purposes, is what our Lua script is outputting as our SGP assembly. This is the appendix in the MP3 write-up, so you have to look and see what type of instructions are being supported and what they're supposed to do. And at least there's a little bit of comments that get interspersed here that show what we're attempting to do here. If you think back to your 381 days, nothing here should look terribly foreign to you. It's different. It is not MIPS. It is MIPS-like, because all of these things are MIPS-like in some way, shape, or form. But for example, we'll see load pointer to an address, and that address should also look familiar because that's our uniform base that's set in our sgp graphics.c file. But load a pointer to that address, corresponding to that X scale float we had as a uniform here. And these two lines of code should look familiar. There was a pseudo instruction in MIPS, which was our load immediate or load address. It's basically the same exact thing is happening here, right? Load the lower order 16 bits of our address, and then load the higher order 16 bits of our address, or them together to get our 32-bit address for future usage. It's not being used right away. There's a lot of initialization happening here. And then finally, we'll see we're actually loading that variable based on our address in a very MIPS-like fashion, right? Take the address, those are little brackets indicating the address here, load that from memory, store that into a register allocated as register 18 in this case, and do all the math that's required as part of this. So you'll have the ISA document in one hand, you'll have this output of the shader compiler also open, and then as you're testing it and as you're running this, you're going to probably want to have the binary blob according to it as well. And that's that third and final output of the shader compiler here. I wouldn't be shocked if we find some bugs along the way, but in general, if there's a discrepancy between the document says one thing and I'm getting this output in my binary blob, unless we find a real bug here, we trust the blob, right? We trust the opcodes that are being generated as part of the script. And you can kind of see that even for a relatively simple shader, we are getting a decent amount of instructions back out. That's in hex here, right? So we're getting, for that case, 79 hex instructions, a decent amount of instructions associated with what's a relatively simple shader. We went for clarity and simplicity versus trying to compact things as much as possible. So that's the shader compiler side of things. And you're definitely going to want to have a member of your team really become an expert on what's happening there and becoming very knowledgeable about how that entire compilation flow happens, what gets put where in memory, and what that means from an architectural design perspective and to influence the design decisions that are happening as a team. In the interest of time, I'll just briefly also show what you're getting from a hardware core perspective in MP3. You're going to get basically like an MP2, just a new starter IP core. This is our SGP Vertex Shader core open in Vivado. And there's a lot of different ways you can look at it, but you can certainly just view the source. The top level source for it, it's a lot to take in, and we'll look at the interfaces for it because it's including a lot of different interfaces. So kind of similar to a couple of the other cores, you have to really scroll quite a bit far down to kind of see where the actual implementation logic actually begins here. And in this case, this top level code isn't doing all that much. It's doing some interfacing to the multiple interfaces it has here and setting some sane defaults for that. Otherwise, it's a very simple state machine where it's waiting for, it's called wait for program. It's waiting for a new program counter to be initialized, and that's how it'll know that, okay, I have a valid program. There's other ways you could do that. I'm open to other suggestions for how we tell it to start, letting it know that you have a valid program. This is going to correspond to the call in OpenGL GLUse program. We're going to want to tell it that it has a new program counter when that happens. And then it's going to be processing vertices not so dissimilarly from how your MP1 and your MP2 modules have been doing so. Waits for that T-valid, latches an input vertex. The difference now is that this core, this VHDL file's responsibility, this module's responsibility is just for doing that latching, and to tell the actual implementation that you'll be responsible for to get started, to run a program associated with that single input vertex, and let me know when you're done. Run your program and let me know when you're done. So this very simple, you can think of it as 4 states, but really this three-state cycle is wait for vertex and tell program to process. Wait for the program to be done and grab output result and actually store the output result. And that still leaves the majority of the additional functionality to this vertex shader _ core file here, which we've just started for you and not really done that much for yet. This is going to be now, in a sense, the entirety of your 381 final project in a single file. But if you follow the same kind of design patterns we have been doing so far this semester, it's not going to be a significant number of lines of code. It is going to require some careful design along the way, and design first and code second. And it is going to require a decent amount of simulation and testing before you want to really try any of this on a board. By default, the code we provide you doesn't run any instructions at all. It gets wait to start and then decides that it's done. So you'll have to rip some of that out. Waiting for start is still okay, but we can't just be done as soon as we receive a new vertex. We have to, in fact, check the next program counter and fetch the instruction and decode the instruction and execute the instruction. All that should sound somewhat sort of vaguely familiar to you from your computer architecture background. So you're finally getting a chance to really explore that. The ISA provides pretty strong direction as to what your architecture has to look like, but it doesn't really tell you anything about the coding style you're using to implement it. So you still have a lot of decisions that you get to make as a team for what is the most appropriate way to implement this module. This code is not at all done for you. It just has the port mappings, a very basic state machine, and you're really on your own as a team to collaboratively design and implement what this implementation for the SGP Shader ISA is going to be. And finally, I'll just mention, because I don't think it's that obvious, a couple design decisions we've been making all semester long have really dictated what that little core's interfaces actually need to be. This is the elaborated view of the design, which sometimes provides some guidance as to what's happening, other times looks like spaghetti like this. But this is the individual SGP Vertex Shader Core module just zoomed in here. And there's a couple things I'm going to want you to know about this. When it's time to start designing your microarchitecture, don't fight the ISA. We have to support the ISA that's there. And it does have some implications for what this design needs to have. If I were to draw this design at a top level, you're going to see why the file, frankly, was just so large, right? First off, unlike in MP1 where you had to interface with the data cache, for this module here, we're going to have both. We're going to have both an instruction cache and a data cache that you're going to be interfacing with. And that probably makes some sense, right? So data cache for the same reason as before, because we have data and we're going to want to be accessing that data relatively efficiently. So we have our data cache. And we also have our instruction cache. If you look at the interfaces in the code, it's using the same library I used for the MP1 data cache for the instruction cache. Some of the signals are renamed to make it more obvious that you're doing reading of instructions versus reading and writing of data in your data cache. But the interfaces are very similar. If you took the time to understand how to interface for MP1, you'll just have a little bit more of that code to understand for MP2. At first glance, this is very similar to our 381 style interface here. We have data cache, we have instruction cache. We also have the registers. I would label this as your config/status registers, or at least, given limits of space here, config registers. These are going to be different from your ISA defined registers. These are the AXI Lite interface registers, right? Things like setting the program counter, checking the status, reading a debug value so you know you're on version 29 of the core versus version 28 of the core. Those are still going to be there. We still will want to use them. Don't be afraid to change and expand and make different ones for this core. Have fun with it. For this ISA, and this is not something that really OpenGL dictates, but to allow this core to relatively easily kind of just slot in with the rest of our processing pipeline, we're also going to have the FIFO interfaces here. And that's what I was showing when we were zoomed in here. It's the array type of our SGP types, vertex type options. And we have an input vertex to our core and an output vertex to our core. That's that two-dimensional array type versus the 512-bit vector type or the record of record types. This core is going to have explicitly an input FIFO and an output FIFO. Input FIFO is going to be driving our input vertex attributes and the end result of our program. And so the very end of each program is going to be based on the transformations that have happened for any of those 4 attributes, for any of those 16 Q16.16 values, set them to the output FIFO. So if we were to draw this core then, and where your logic is going to fit, it's got a lot going on here. Your core now, your Vertex Shader core or your implementation, your logic, is sitting somewhere around here. It may need to be able to read some configuration registers to configure it, maybe for different testing purposes, at the very least perhaps for the program counter. It's got some configuration information that our infrastructure has it set by those AXI Lite registers. It has in FIFO. By doing in FIFO and as well as out FIFO, again, that wasn't explicitly a requirement. We could have this doing vertex fetch as well for us, but we have a separate vertex fetch module. We have separate modules for doing viewport transformations, and they're all interfacing on that same kind of 512-bit FIFO. This allows this core just to slot right in. The top level of Avado design that you're doing in this is maybe 10 more minutes of work than it was for MP2. It's 10 more minutes of work because there's a lot more things to hook up, right? We have to hook up this. So this and this, you know how to hook up. And now we should draw, a top level box over the entire thing, right? So based on your MP2 experience, you already know, because the core had the same exact thing going on, how to hook up my AXI light register, how to hook up my input FIFO, and how to hook up my output FIFO. You're doing the same exact thing for MP3. And then now we're also hooking up, similar to what is available in MP1, but you weren't doing the hooking up there, an actual data cache and instruction cache, which is going to be hooked up differently. That's not hooked up to our AXI light registers anymore. That's hooked up to our memory interface. We're going to add some more ports to the memory interface and make sure that all gets hooked up. But it's a relatively straightforward thing. But now our core has all these interfaces that different parts of the ISA are going to be requiring. We're going to always have a fetch, right? So if we were to start to draw this out, we're always going to have some sort of PC logic, right? That doesn't go away. And based on our PC, we should be doing our address calculation for fetching. And then you're going to have either a stage and a state machine or some combinational logic. We're going to want to do our instruction decode, as well as potentially in parallel our register fetch. This should start to sound familiar, right? Even though this is an attempt at a SIMD architecture where we could do multiple operations in parallel, it still follows the same general organizational layout. So instruction fetch, decode, plus some register file fetching, followed then by execution, where execution could be calculating of addresses. It could be doing actual logical or arithmetic operations here. And this is where we have the SIMD architecture. So we're doing up to 4 things at one time in that execution stage. There's then going to be the memory stage. This should sound vaguely familiar to you. There's then the memory stage, where we're interfacing now with data memory. In theory, we've calculated the right addresses. For the most part, we're using memory to read uniforms from that region of memory, but we can also have shaders that are just writing to arbitrary buffers in memory. It's all the same unified address space. When your logic is wrong here, things could break in really fun ways, but keep the address. Make sure your address calculation logic is roughly correct, so you're not just spraying data all over our memory in the system. And then finally, we would have potentially that write back stage where we're updating registers. Final thing that's not being shown here is we do then have those special instructions for reading in values from our FIFO and writing values back out in our FIFO. That's our little extra thing that I think a modern Vertex shader wouldn't require a FIFO read and FIFO write. This allows it to plug in so easily to the rest of our infrastructure. So there is a lot here. Long story short, have a driver person, have some micro-architectural design decisions, but make the design decisions at the paper and pencil level, and then the implementation is a separate thing. So you'll have to become fluent in the driver, you'll have to collaborate as a team to make some good design decisions along the way, and you're going to be spending, hopefully, a lot of time in simulation, saving the board tests for kind of the fun stuff near the end of this assignment. I'm really excited to see what you're able to come up with, what bugs you're able to find, what changes at the last minute we have to make. It should be really fun. So I'm looking forward to it. Always let me know if you have any questions as you get started on it.